All right, so, let's try it one more time. Okay, so last time we started dealing with functions, if I recall correctly. And if you when you log in, please mute yourself. Okay, let me do it. There we go. Okay. So we talked about uh, the new syntax for functions, mentioning that all the functions that you are working with, that you can actually okay, someone over there keeps coming online and okay, we good? All right. One more time. Okay, so we first talked about how the functions, the new signature of the functions, which you add the return statement post declaration of the function. You start with a nodo, and we said in future you're going to know why we need that, because sometimes you need to decide what the return statement is at compile time, and it needs to know what it's going to return based on the compilation that is happening, and therefore you're going to need that. We created that getInt thingy, and we talked about getInt being validating something. We said if you are writing a getInt function is supposed to validate something, we have to keep changing the validation for the value that we are receiving and recompile the code. Therefore, either we have to write a new function, each different types of getInt function, and each one does a specific validation from scratch, or we recompile our code, which wasn't good. Then we mentioned that like arrays, function names hold the address of the function in memory, which is essentially the code that resides in memory and CPU executes. It holds the address of that. It's not data. It is data, but it's not raw data, but it's the CPU instructions where execute a function. So you can actually print the name of a function, and you can know exactly where the function is in memory. That gives us this advantage because since the name of the function is actually holding the address of the beginning of the code in memory, if I could create a variable that holds the name of the function, then I could simply pass logic to different functions using the address of the function instead of calling the function. And we demonstrated that you create a pointer to a function by literally writing the prototype of the function and put the name of the function, name that prototype for your function pointer, put it parentheses around it with an exclamation mark, and then that literally becomes a pointer. So at line 17 over here, I have a pointer to any function that receives two integers and return void. Obviously, because it's not used, I initially set it to null PTR, but then I can actually, one by one, set it to different functions, and using the same function call, I can call different functions. So at line 18, I'm setting it to sum. So funcPTR at 19 will call the sum. At 20, I'm setting it to prod. funcPTR over there will call the prod, and so on and so forth. Having said that, we said we can even create an array of pointer to functions. So essentially now I have 3 pointers that can hold the address of any function that receives 2 integers and return a void. Therefore, I can initialize that array at line 17 to sum, prod, and repeat. So essentially, funcPTR0 holds the address of sum, and funcPTR1 holds the address of prod, and funcPTR2 holds the address of repeat. And if I put the function call inside a loop, 3 different functions are going to get called in each iteration of the loop. So that brought us to another fact, that the parentheses after the function name is not within the syntax of the grammar of the language, but it's actually an operator, exactly like the index operator. The index operator, when you put it in front of a pointer, you're essentially saying how many scalars add to that pointer. When you put parentheses in front of a function, in front of a pointer, you're essentially saying that I want to call whatever code is sitting over there, and I want to pass whatever I put between the 2 parentheses to that code. Yes? It doesn't work that way. It works with a stack. So it does not at all know what is the size of the function at all. It knows where the function begins. But at the end of every function, there's a return. So this is what happens. Give me a second. So we talked about stack the other day, and we said like a stack is essentially a struct. Supposed to scene 1. There you go. So a stack essentially is first in, last out type of an entity. So a stack is something like this, okay, and you push numbers to it. So if I push 10 in it, then I push 20 in it, then I push 30 in it, and I push 40 in it. Now, the only place I can pick stuff up is from the top. So each insertion is called a push. And so on and so forth. And when I remove something, it's called a pop. So if this stack is called S, if I say A is equal to S.pop, A will have 40 in it. And the 40 will be removed from the stack. OK? And if I do another pop, A is equal to S.pop, it pops another one in here. Therefore, this will be 30, and this 30 is removed. OK? So that's how the stacks work. You push stuff in it, you pop stuff out of it. Are we OK with this?
Yep.
People at home, are we OK with this? Thumbs up, please, if you're OK. OK, now let's see how the functions are called. Why am I explaining this? What it has to do with any function at all. OK? Now, so we understand what stacks are. A stack is a data structure in which you can enter data using a push, and you can pop. Anything that you push in first, you pop last. OK? We are OK with this. So as you were mentioning, the size of the thing. Let's say this is my memory. First of all, let me see where's the, OK, I can go right down to, I want to see how far I can go so I don't, OK, good. All right. So say this is my memory. OK? And Here's my executable. Okay? This is address 10. This is address 20. This is address 30. This is address 40. Okay? Let's say from 10 to 20, the function foo is sitting at. Okay? From 20 to 40, the function fa is sitting at. And over here, I have main. Are we clear on this? People at home, are we OK with this? All right. So when you actually start your program, when the compiler starts your program, what happens? Any function call dictates the computer, the compiler, to push the address where the function is called into a stack. So this is my stack. And let's say in here, I'm calling foo, I'm calling fa, and in here I'm calling foo at this point. And this is address 30 that I'm calling foo. In here is address 50. In here is address 70. And in here I'm calling fa again. And that's address 80. And I want to run this code. OK? So when the code is actually running, compiler starts main. When main starts, what is the address? 40, right? Now main starting. It comes to foo. Foo is called. What is the address of foo?
10.
50.
Okay.
Where is it sitting? Not where it is. 50. So 50 is pushed over here. It knows where foo is because foo is holding the address of its beginning. It doesn't need to hold it anywhere. OK? So it goes to foo and starts executing foo. Right? As soon as it reaches to the end of foo, what command is called? Return. Even you say it or not say it, return will be called. Return is a pop. What does it pop? 50, right? Goes back over here, and 50 is removed, continues the execution. Comes to fa, wants to call fa, pushes that one into the stack, 70. Goes to fa, executes, reaches to foo. What is the function called at foo? 30. Pushes 30, executes, reaches to a return. When it, executes, reaches to a return. What's going to happen? Pop. 30 is popped, goes back to 30. Runs, reaches to another return. What is popped? 70, jumps to 70, keeps executing. Comes to fa. Fa is called 80, pops in here, goes to 20, keeps executing, comes to foo, 30 is pushed. Goes to 30, runs, pop. It pops it, comes back over here. Runs, pops it, goes back over there. Goes and pops it, main is finished. If there was no stack, there was no function calls. And it has nothing to do with the size. It's your return statement that dictates go back. And it knows exactly where to go back using the... Have you ever written a program that by mistake you called a function in a function and the function again in the original? So essentially you did this. So foo is calling fa, fa is calling foo. It keeps pushing the stuff into stack forever. Then your program crashes and says stack overflow. Now you know. See, one question you asked that led to this one, but I had to explain.
No worries, teacher. Actually, I didn't know that happened on the back end.
Oh, it does. That's it. Literally the way execution happens. Now, when I get to recursion, that's going to bake your noodles.
No
OK. OK. Oh, yeah, go ahead. What else?
No, nothing for my part. It's just that I remember when I was, I used to use the HP calculators, and they also have a language that is by default that works by stack, but it's more transparent. This is basically
But this is universal in all programs. OK. Now, C++, when I said in C++, in C, when you learn something, it applies to everything, does an array know what a size is? No. That's exactly with an array. But an array, that's exactly with a function. But a function has a return mechanism, an array doesn't. That's why we have to create our own construct for a good array. Right? Are we OK? People at home, are we OK? All right. So now that the function calls are done, so we go back over here. Anyways, I was saying that what I was saying. Yeah, I was saying so like this, I can serialize function calls in an array and in loops call different types of functions. I can even do better than that. Instead of actually writing a get-end program that relies on different types of, that relies on programmers to write several integer input entries, I can create one and simply pass the address of the validation to it. And even if, so if they want to get an integer with a validation, they pass the address of the function of the validation to it. And because we actually dictate to them, this function works with a validation function with such prototype. So they know they need to create a validation function that receives whatever and returns whatever. And they pass it to the function they have. And we can even make it better by setting that thing to be null PTR by default, saying if you don't provide it to me, it's null pointer. And then in here I can say it is valid if is valid is null or yada, yada, yada. OK? So if they don't provide anything because it's valid is null, it means no validation. It means we're done. If is valid has some value, we talked about lazy evaluation over here, right? We drew it, right? Same thing. If this valid thingy becomes false, then it has to check the second one. Therefore, the function validation is gone. So like that, I can save lots of time. Oh, sorry. Yeah, so this one has the mechanism over here. It also passes a string to set to the error message and all this stuff. So we made it a little fancier. Are we OK? We're OK with this? All right. Now we said C++ doesn't like doing low-level stuff. Because holding the address of a function and telling to CPU to stop and go somewhere else in such a low-level thing, it is extremely non-object oriented. You're not only having a standalone function, but you are calling the function using its address. That's very low level. We don't like that in C++. In C++, we want everything to be object-oriented. So they said, you want a function, you have to encapsulate it in something. So what we do, you're allowed to create a class for your function, that class that is supposed to represent functionality only. It's not a class to encapsulate an object or something. So that's why they're called function objects. The purpose of them is to accommodate a special function. And we call that, for example, class adding, which means the adding class is supposed to accommodate adding two things. And I overload the function called operator saying that an object of type adding can be used to call two integers and yada yada. And you can overload that with many different things as you are going through. So we could have this something like this. Float, 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 and double, and double, and double, and you can overload to whatever you want. So because it is a function call, you can overload it to whatever you want. And now this functor of mine provides three overloads of addition. Okay? So if you instantiate the function adding called add, now you can say add number of calls, how many times it's called. Because it's an object, you can actually have something in it to count how many times you're doing something. You cannot do that with regular functions. And then you can add whatever you want using the function call operator. So as soon as you put the operator after the object, your operator overload will be called, and these are passed to those functions, and yada yada, and the rest is obvious. And that's functors. Are we okay with this? You okay? So a function object or a functor is a class that overloads the function call operator, and that's it. All right? You okay with this? Now, we have rewritten the exact same thing. So in here, as you see, I have a class for int validation. Then I have a class called isAdult that is the child of int validation. And then my int getInt receives a reference of type validation, and it calls that one. Now, if any children of int validation that implement the operator over the operator function call, they can actually call it and do the validation. So as you see, it uses the exact same thing that C language does, but in an object-oriented way. You're passing an object reference, and then whatever that is needed can be done in there. Does that make sense? What is this thing? Oh, pointer to templates. Oh, yeah, yeah. So there's nothing special about pointer to templates. Is this? Yeah, there's nothing special about pointer to templates. Templates are simply functions that are generated by compiler. Where does noises come from? Anyways, so yeah, so again, everything that you learn in C language applies to all the aspects of the language. When I say pointer to a function, it is any function. Now, that function could be a templated function. It doesn't matter. So when I actually create a function template over here for ascending and descending, and I'm using it over here in sort, to do the comparison, whatever it is. Am I doing this over here? Yeah, I'm receiving the comparison over here. Okay? So because these are all templated, when I actually want to call the sort, then I have to say create of the object called create the function of type integer for the ascending template and pass its address. It doesn't make any difference. It is a function, but it's created by the compiler. So pointer to a function template is the exact same thing as a pointer to a regular function. The difference is that you have to just write the proper syntax for its name. But the rest are all the same. You okay? Then we came to lambda expressions, and we explained as an introduction for lambda that lambda expressions are very small little functions that you want to write it only once, and you want to simply, you don't want to write the entire, for all those validations that we have, they're very little functions. You don't want to actually go and write a function and add a prototype and all this stuff. You just want to get an integer between 10 and 20. If you want to do something like that, you don't have to bother yourself to go actually create a function separately for it. You can just write a function right over there inside the argument of the thing. How do we write a lambda expression? Actually a small little function, one-liner function. You actually put a square bracket. That means that in that square bracket, you're going to tell it how to access the scope, the variables within the scope that is being created. We'll find out soon. And then the function call is there, passing values, not passing values, exactly like a regular function. So assume that the square bracket is the name of the function, and the rest is just the function. Now, if you are a wise person, you're not going to write a lambda expression that is 300 lines of code. You could. It's just, come on, write it somewhere else. Don't make your code ugly, OK? You could, but don't, OK? Because the type is, the lambda is created on the fly, it's not something that you can have a type for it. You always use auto, and you put if you want to name it. If you need, like if I want this hello thingy to be used in main only, and that's what I do. I say auto hello. The hello becomes the name of that function. I can call it over and over like a regular function. And we mentioned when we actually have that is valid thingy that we wanted to run with the pointer, it's very easy to call the function, the getInt function, like this. Say, OK, I have a getIt function, and I want the number that I have to be greater than 18 that returns true. So this essentially becomes a function, and the address is passed. OK, right in the function call. You don't have to write a separate one because it's very small. Same thing like here, a number of students. I want the number of students be between this and that. You do the same. So again, I am writing one-liner functions, but the syntax is like a regular function. If I had to write over here several lines, there was no problem with it. You can do that. You can literally write it like this and keep going. There's no problem with that. Or you could have just put it right over here, inside here, your choice. But again, if the functions are getting too big, don't write a lambda. Just write a function. All right? You're good? And that was the last thing we talked about. So I'm going to call this and that's the first thing we are talking about today. Do I have an address in here? No, yes, I do. I have to fix that. So copy. This is everybody's OK? Are we OK? All right. OK. Lambda syntax. So So this is the syntax of the Lambda that we have. So we have the capture clause going between the two square brackets in the Lambda. Parameter lists are exactly the same thing as regular functions, and return type comes always after. If you don't mention the return type is what your function returns. So if your function returns an integer, then it's an integer. If it's not, it's not. So if, like, here we are actually mentioning that it's an integer. If you don't put that int, it's because a plus b is an int, it will be int. Okay. The capture clause tells you how the neighboring variables are to be able to be accessed. So if you don't put anything in there, that means no variables are captured. Everything inside the Lambda belongs to Lambda and has no access to what's coming from outside. If you put an assignment, that means I want to receive all the variables that are within my scope by value. So you can have them by value, change it in your Lambda, and it's not going to change the values outside. You follow what happened? No. If you put ampersand, it captures all the variables by reference, which means if you change it in your Lambda, the neighboring variables will change. You can always list comma-separated names of the variables to tell which one is accessed by what. So in here, x is accessed by value, y is accessed by reference. That's that. Very straightforward. Parameter is the same, return type, if it's submitted from the return statement. But again, if you have two return statements, one is returning a double, the other one is returning an integer, you better have a return type. So it knows which one to cast it to, which I hate. You're not supposed to have two return statements. But if you do, and one is double, the other one is int, then probably it's going to upcast the other into a double. I don't know. I've never done that. I never do multiple returns, so I really don't know what's going to happen. Try it. Okay, have two different return statements with two different values. Probably it's going to cast it to the, like when you do a plus b, the two, they're not the same. One is upcasted to the other one. It's probably going to do that, but I don't know. So it's always my suggestion is, in programming languages, especially complicated programming languages like C++, don't leave anything to default. It's not very difficult to write the function and an arrow and the return type. Write it. Don't leave it optional. Oh, I know it's going to return an int. I'm not going to just write 5 characters. Come on, write an arrow and put an integer over there to make sure that you're not going to have a bug. Okay, and also, poor person is supposed to come and debug it after you. Doesn't have to look through your return statement to see what the devil is going to get returned. So it's always be specific and don't leave stuff as is. A demonstration for future. It's not what we are doing now. I just want to show you why we use Lambda and what does it mean to use STL. We learned templates. We learned functions and functors and Lambdas. I just want to show you why we are doing this. Let's say you want to write a program to sort a series of stuff in a function, in an array. First of all, you don't use an array. We created an array, right, and templated it, right? So what we can look at this. First of all, you don't use an array. You use a vector. Vector is an efficient array. So you're going to say, I want to have a vector of integers, and these are the values. Then you're going to say, please sort them from the beginning to the end using that Lambda. Done. All the things that we learned is going to end up to this. You learning how to use templates, because now you know what templates are. you to use standard template library. That's in your algorithm. So the library that we have, sort is in the algorithm. And it receives two what we call iterators. We're going to see soon. Exactly like range-based loop. The range-based loop, the thing that you put at the beginning, that's called an iterator. Okay? So essentially you're saying iterator that points to the beginning, iterator that points to the end, and now sort. And you are giving the condition to compare the two elements of the vector, and it does it for you very quickly. And soon we're going to learn how we can actually ask it to do it in parallel. So not only do it in one process, or you want this thing to happen in 10 processes parallel so it sorts it faster, something like that. Okay? You can do all these things. So that's why I call this a look into future of what we are doing. So essentially, if you educate yourself with standard template library and go through it and try a few of them, when you are programming, 95% of the time when you see something complicated happens, you know that there's going to be a template that does that for you. All you need to do is to search for it. And instead of writing a ginormous code, you simply use the algorithms and the standard template library to do the things hundreds of times faster than the logic that you want to write. You can never write a code better than those who wrote C++ itself, can you? Right? So it's better to use theirs. They actually wrote it in a way so it's faster and more efficient and all the good stuff. And brings down the speed of your programming much lower, the possibility of crash and memory leak and all those stuff much lesser. Are we good? So let's see actually how the devil all these lambdas work. Oh, this is not the one. Oh, I saved it? Okay. Yeah. So I created this different type of lambdas over here. Add 2 to I. So as you see, it's actually by reference, which means it's going to add the value to the A over here. Oh, because A is captured by reference. You see that? And it returns the value, so it comes out. So whatever you pass to this lambda that is add I to A, it will add the value of that one to the A that is outside. You good with that? The other one, I'm subtracting. I'm getting everything by value. So if I return I minus 2, whatever I passed, it's going to return minus 4. It's going to reduce it by 4. And nothing happens to outside. The I over here and the I over here are two separate entities. The I over here and the I over here are two separate entities. Although it is accepting it by reference, but because you are creating another I over there, that shadows the other one. Clear? Okay, remember, see, again, whenever you are writing any type of code, remember all the previous rules apply. And then you learn new ones, right? So to write this little so line 7 to 9, I have an integer I and I have an A. A is not defined in that lambda. But because it has a reference at line 7, it captures the A by reference. Therefore, it changes its value. I over here is a local variable. It shadows everything that is outside. So the I in here and the I outside, they have nothing to do with each other. Subtract is by value. I'm not going to even go through it. And this one is by reference too. So it is capturing A by reference, but it's not changing it, so nothing happens over there. That's a freaky lambda. So what I'm doing in here, I'm saying get everything by value from the system, whatever from the neighboring stuff, and get a character. You see it doesn't even have a name, right? I'm saying start from 0, go up to A, whatever the value of A is outside. Okay? Print whatever I have CH over here and go to new line. And right when it ends, I call it. So sometimes you just want to run a function. That's a stupid thing to do because you could just write the for loop over here but separate it by itself, but it's possible. So like I could literally write a loop and do the same thing in here. Okay? But for some reason to just show you that lambdas can be called exactly like structures that you can instantiate right at the end of classes. You can have nameless classes that you can instantiate at the end. You can have nameless lambdas that you can call at the end. Do I make sense? Are we okay with this? You don't get what? This one? Okay, it's very simple. Auto star. Okay. Do you get this? Oh, thank you. Do you get this? Thank you. You follow what happened? So I'm calling it star, and I'm calling the star.
The character is, yeah.
Again, think about all this. What does auto mean? It means make this the type of. Auto means make the star to type of whatever this is, correct? I can just remove that. And the whole thing is, so I'm saying pass the star to this logic. And the logic is accepting a character, so I'm good to go. Does that make sense now? Okay. People at home, are we good? All right. So essentially, I'm drawing asterisks over here over and over. So again, different types of examples. So in here, I'm receiving I by reference from outside, while A is passed by value. So essentially, in here, it's going to have A. And if I change the value of A, nothing's going to happen, although I didn't change it, because it wasn't by reference. And then so on and so forth. OK? Anyways, it's just walk through this. I gave different types of examples of all the things. So in here, like at line 52, I'm saying everything is by reference except A. OK? At line 58, I'm saying everything is by value except I. And line 46, I'm saying A is by value and I is by reference. We OK? People at home, are we OK? Yeah. All right. And now, let me bring some good stuff in. 1, 2. The class today ends at 3 o'clock. Anybody wants to take a break now before I continue? Anybody? People at home, anybody wants to take a break? Say something. Oh, I see down thingy and lots of people have no idea. Speak.
No.
I know yours is no, but I see two people are saying yes. So Solar, we want to go Solar, and Parth wants to go for a break. Okay, 5 minutes break while I'm preparing this. Let me pause. Please, I'm recording over here and over here. So we are kind of starting our lecture for today by talking about exceptions, understanding what exceptions are. So I usually do this while students are sitting and explaining. It's easier, but people are at home right now. They can't do it, so I'm going to draw it over here. I hope I can actually do it properly. Okay? So let me just see. Just want to get this to make sure that I have it over here properly. Just want to make sure that the date is correct. And then we'll continue. Okay, so imagine that there are a series of people. We are playing a game type of a thing, and there are a series of people staying alive. So I have a series of people over here standing, or yeah. All right? And what I'm doing, I am throwing a ball in this direction. Okay? Now this guy is responsible to catch a ball. Okay? Now this one is supposed to catch a soccer ball. Okay? And this one is supposed to catch a basketball. Okay? If I throw a soccer ball, who's going to catch it in here? And this is person A, person B, person C. If I throw a soccer ball, who's going to catch it?
B.
A. B will never get anything. Because any type of course, if I throw, I don't know, a marker, nobody's going to catch it. Okay? But any type of ball I pass, the first one's going to catch. So I did not set these things properly. I should set them properly. Okay? What do? I'm going to say this will catch any volleyball. This will catch any, I apologize for my horrible handwriting, soccer ball. This one's going to get basketball. Okay? And now I put someone over here that is going to receive a ball. Okay? And in here, I'm going to put over here somebody who receives anything that looks like a sphere. Right? Now, if I throw a soccer ball over here, B will catch it, right? If I throw a volleyball, A will catch it. If I throw a baseball, B will catch it. Baseball. None of these are base. This is basketball, by the way. I'm sorry for the handwriting. This is basketball, not baseball. Okay? So baseball, we will get it. If I throw a football, depends if you're in England, soccer. But if you're, I don't know, North America, B is going to catch it, right? If I throw a globe of Earth, then D is going to catch it. Correct? If If I throw a chandelier, nobody's going to catch it because it's not a spherical thing, right? Do we understand this? People at home, do we understand this? By the way, oh, sorry. Oh, there you go. That's the sphere up. And now the ball is not visible because of the light. Shoot. Yeah, that's, oops, now. It's like, I don't know. This is volleyball. Anyways, so yeah, so people at home, are we okay with this? Nobody's answering. Can you hear me at home? Anyone?
Yep, we can hear you.
Oh, okay. So nobody's giving me thumbs up, thumb up, so I don't know if you got this or not. But anyways, so this is called exception handling. I do not like it. Many companies, they don't like it, but it is in a syntax of the language, and you can use it. Okay, essentially, one thing we need to remember about exceptions, I'm going to write you the code for it, a very basic code for it, and then I'm going to write a more sophisticated code so you know what I'm talking about. Exceptions are what they are. Exceptions. They are not part of your logic. No exception happens through logic. Exception is something that you don't expect, and that becomes an exception, right? It's an exceptional thing. So you cannot use this for your user entry. If user enters something wrong, that's highly expected. That cannot be an exception, right? If you want to open a file and the file is read-only, that's highly But if you want to write a file and you see hard drive is not responding, that's exception. Exceptions are things that you don't, it's highly unlikely to happen, and you have to disrupt the normal execution of your program and do something crazy. I'm going to write you the syntax for it, then I'm going to write you the proper thing for it. Not a proper one, but you'll see. Like, if you include exception header file, yes? It is a special type of error handling. It is exceptional errors that you handle. For example, if you include, I think, new header file, then your new will not return null anymore. If something goes wrong, it throws an exception. Memory is not enough, it throws an exception. You can do that. Okay, but we have both mechanisms. Let me just show you the syntax for it first. So the code I'm writing right now is only for syntax purposes. Writing a code like this is only good for walkthroughs, so I see if you understand what's going on, or, I mean, like, you don't do this. You don't do exception. Like, exception handling is when your program is supposed to read something from memory and you're going to someone else's memory. That's an exception. And you see your program crashes and memory gets dumped into, you see that, like, exceptional stuff. You can actually catch that. So if your memory is failing, you can catch it and do something about it, not to terminate your program. So things like that you can do. So any exception any throwing of an exception should happen in a try scope, try block. So you create a try block, and inside that try block, an exception should be thrown. Now, exceptions could be thrown outside of a try block in a function, but then that function should be called inside a try block. If you, so let's just for now take a look at the syntax over here. So I have a try block at line 9, goes right down to line 18. You see that? Okay, and then I have series of catch statements underneath. The reason I'm saying it's very unusual type of execution is that when try is happening and I is 0, it comes to try. It reaches to line 10. You see that? When I becomes 0, if statement becomes true. And at line 11, D is thrown. When D is thrown, everything after D is completely ignored. It's a go-to to where you catch the type of D. D is a double. Wherever you are catching a double, the execution is going to end there. So when this program is running, as you see, when it reaches to throw, it jumps to double. And everything after that is completely ignored. That's why it's very dangerous. If you throw an exception inside a function, return statement, and everything is going to go down to drain. So I don't even can understand what the logic is going to look like. That's why I'm saying you have to be very careful with using exceptions. Okay? So this is completely ignored. It comes to catch, and the double thingy happens over here and says double exception. And I'm going back up. Now in here, as you see, a constant character pointer is being thrown. And the closest match for it is a constant character pointer. Therefore, it comes to it and executes that one. And this is now ignored. And at the end, when neither of these two if statements happen, it's going to throw an integer, which is going, remember I said sphere? When you put 3 dots, it means if anything is thrown. Whatever that is coming in, I'm fine. It catches that. So if you don't know what type of exception you're receiving, that's going to be there. And as you noticed over here, line number 20 will never happen, ever, because I have 3 throw statements in front of them. And the compiler is not giving me an error warning anything. Again, exceptions are used for exceptional matters. OK? Are we OK down to this point? So I could have had something like this over here. Somebody help me spell double. So as you see, as I mentioned, this throw is not in a try statement. And if you call this function outside of a try and it throws, the operating system is going to catch it. And it's going to tell you your program ended with an unhandled exception. And that's always when you go out of your memory and you do stuff like that because you didn't catch the exception. It always crashes your program. That's the reason. OK? So now if I run it, you will see that the craziness comes to that. So when I actually, stop. So when I run this program now, as you see, it comes down over here, goes to here, and as soon as throw is executed, it jumps to double. Now imagine if this throw was in some other file. How you want to walk through that? OK? Careful. Now let's take a look. Not that, take a look. Cannot change the solution property while debugging. Oh, yes, ma'am. There we go. Set as startup project. So in here, I have a class called int.h. Int is supposed to keep a validated integer. So I'm writing a class because integers are not sufficient for me. I'm creating a class for it. So what it does, it has a validation function over there that validates it, and I have get and put to get and put the value of the integer, whatever I want to do. And these two operator overloads are using the get and put. Are we okay with this? Are we okay? And if I actually show the integer over here, we'll see that it's not a very good design because as you see, this integer can only validate a mark. We have a problem in here because the validation that we have over here is there. So I'm actually replicating how I taught you what pointer to functions are, but now object-oriented. And we're going to go through it and see exactly what the differences are. So the validation function over here is checking marks to be between this and that or whatever. Are we okay with this? And now when get is happening, the get will actually check the validation and do whatever that is needed to do the validation. So the get function over here receives the value, does the validation, and then continues the thing. So essentially it says, if validation is returning true, then I'm done. If it's not returning true, then go back and do the data entry again. Are we okay with this? Now, the next step, what we are going to do over here is to see, and this is, I've written this long time ago, so sorry for the, whatchamacallit, that safeguards. It's just, now we're going to do the exact same thing with function pointers. Okay, and I'm going to progress and go forward right down to exception handling. Okay, so still I have the integer, and life is beautiful down to this point. So I'm going to open this one, and open this one. Now the difference between these two is that is that too small? Can you see back there? People at home, can you see? No answer? Hopefully it's a good answer. I don't know. Anyway, so what you see, as you see over here in my integer, instead of actually having a validation function, now I have an address of a validation function that sets a message for me and receives an integer and returns a Boolean. And by default, I set it to null. And the constructor of my integer will actually receive the address of the validation. So now I can create the integer object, passing the validation to it, and that object becomes, that integer becomes an integer that is validated as such. One more time. mValid is a pointer. This pointer is a type of a function, any function that receives an integer, a string to set to error message, and returns a Boolean. And by default, I set it to null. It's a property of my class. Here I have a constructor. In my constructor, I am receiving an integer to initialize the value of my m value for the integer. And also, I'm receiving the address of any validation function that receives an integer and a string reference and return a Boolean. And I'm setting my value to the value and my validation to the logic. Now, in my get, all I need to do is to make sure that the validation is either null or good for me to be done. The logic remains the same. Nothing is changed. But the usage is more elegant. It's kind of a mixture of object orientation and structured programming. So when I look at my main now, this is how the main works. I have a valid age. As you see, my valid age function works as such. It receives an integer and a string, goes through validation, sets the message to whatever it is supposed to be. That's valid age. This is valid mark. And now what I need to do in my main is simply say, I want an int called val that receives 0 and gets a valid age. So val is received is age. Oh, shoot. Why did I do that? OK. I thought I created two, but it's one I'm setting a different one. So now I'm saying val. I'm passing valid age. So initially, the validation logic of val is pointing to valid age function. Therefore, it can be used for age validation. Now I'm going to call the set function that sets the validation function to whatever it is. So here's set. As you see, set function receives a validation logic address and sets the m valid to whatever that is. So now I can set the validation to valid mark. And now when I actually use cin to get the value for the thing, it's going to be a mark. All right? So essentially, if I run this program, so that's invalid integer. Try again. I'm going to put 2 over here, too young to drink. Next, please. OK. Now in here, I'm going to say 21. I'm going to say, good. What would you like to drink? Now enter the mark. I'm going to put over here -10. Invalid mark. That's the thing. So as you see, the validation function, everything is in action. And now everything works perfectly. Got it? That's using pointer to functions. Next. They are all the exact same logic, applying different methods. So first, we have done it the crappy way, which is just an integer does something. The second one, you can do anything you want with it, but is structured, is not object-oriented. Now, we're going to do this. This is a much better one. Set as startup project. So now, I have a class called validation, which is an interface. It's a functor. That functor says any validation must be child of me. It must have a function call that receives a val and a string. Anybody who wants to do validation must inherit from me. Now I'm going to say class valid age is a child of validation with minimum age and maximum age. And the constructor sets to 19 and 100 by default. I can set it to something else if I want to. And then the Boolean operator, yada, yada, does the validation, which is the minimum and maximum. And valid mark validation only overloads that one. It doesn't have any constructor even, because it's always between 0 and 100. OK? Now, if I look at these functors, the functors implementation are exactly what we expect it to be, which essentially says the constructor at line 4 is setting the minimum age and the maximum age to min and max. Valid age operator receives a val and a string and does everything that is supposed to be done with the minimum and maximum values. You okay with this? And if we look at valid mark, it's the exact same thing. Now, how do we create the integer for this? The integer of mine looks like this now. I'm going to say I have an address of validation. Could have had a reference to, but I made it anyway. But because I want it to be null too, that's why I did. But anyways, never mind. So set and get. So set sets the validation, and everything's done and perfectly good. Now in int.cpp, all I need to do in my constructor to set the address of validation object to the validation functor that is coming in. And everything is virtual, and the proper thing is going to be called at when it's being called. So take a look. I'm saying mvalid, call it, and it's done. As easy as that. Or I could make it a copy and do a copy construction out of it and set it to a default validation of my own if I wanted to do. So you can have many different ways. It's an object. Do whatever you want to do with it. Okay? And calling that, creating the, using the validation happens as such. So essentially, you create a valid age, kids age 3 to 7, valid age adult 19 to 100, and valid markers like that. And you can call your int with any of those that you want. You pass the functor to it instead of a function, and it works same way. Are we okay with this? You're not going to get it in 3 seconds now. You have to go home, walk through every single one of them. And they're all functional and they work. Open the Visual Studio, do F10 one by one, go through step by step, and you'll see exactly what's going to happen. If I do it now, we're going to stay at function in the next 3 weeks. I don't want that. Okay? I want to be done with this. Okay? So please go through this, and you'll see this is with functors doing the exact same thing. Now, because all these things are too much, I want to do my stuff much easier and quicker. So what do? Set a startup project. I create my class exactly like I did for C language, which is a pointer to a function. Okay? As simple as that. So the class is the same thing as the pointer to function. But main is a bit different. So the best way to do it is this. You see that? I'm saying int mark, and it's receiving the validation for a valid mark using a lambda. Int age, receiving the validation. This is not a good one. I should have created it out there, but anyways. It creates a validation using a lambda over here for age. So between, and this is the validation for it. And inside main, I call it. Age is that, and mark is that, and it works exactly the same way. Right? So you can use the pointer to function and simply pass a lambda if your functions are small. It's not a bad example, but you can do that. Or you can use a functor for it. They all work the same way. And last but not least, awful example for exceptions. You never do exceptions for user entry. That sucks. You don't do that. But I'm just writing it for you to see how exceptions are designed. So in here, I'm going to set a startup project. . So I create, first of all, I include exception at the top. Mother of all exceptions is called exception and is inside exception header file. Okay? And it has a method, virtual method that you can override called what? Essentially, it returns a constant string which what went wrong. Okay? And I have a message over there. So I'm saying bad integer exception is a child of exception, and it's invalid, yada, yada. Then, remember ball, basketball, baseball? I'm creating that over here. Next one is too young exception, which is a child of a bad integer exception, which it has a public too young exception. It is the constructor that we have. And as you see, there's no message of any kind in here. I'm just creating a hierarchy of different shape of classes so I can recognize them when I'm catching them. When you look at it, it's the same thing. With a volleyball, it's just a soccer ball is very similar. Right? It's just the pattern and stuff are different, let's say. It's the same thing over here. So too young exception is a bad exception. Too old exception is a bad int exception. Bad mark exception is a bad int exception, and so on and so forth. So now for my validations, I have different types of functors created over here for validation, as I did before. But the difference is that my functors for validation now will not handle the error. They will procrastinate. So I'm saying get, if the value is like this, clear, and throw bad exception. I don't want to handle it. Someone else will. Which means the burden of validation now goes to main, whoever's using this. In here, I'm going to say, and as you see, it throws an exception with bad int, because that get int is doing that, whatever it is. Okay? So that's my int, and the validation. As you saw, I show you exactly what they are. And these are the validation functions that we created, as you see. So the valid age throws too young exception or too old exception if it's less than 19 or more than 100. It's not going to handle the error because it's an exception. An exception is not supposed to be handled. It's something rare, and I have to always reuse the word exception. It's something that doesn't happen usually. So that's why you don't handle it. You pass it through. And the same thing over here. Now, in my main, I have to handle it like this. It makes it extremely ugly. So what happens, they say that you separate the business logic from error handling. I don't know if that makes sense. So all you need to say is like, get the age. And then it's a catch too young, catch too old, catch bad exception, catch exception. It goes through all these. And you handle the errors afterwards. You try getting the age, and you go through. Okay? And that's the reason you put no except after your move logic, because they are not supposed to throw an exception. They're moving stuff. You cannot put them in a try statement. And that's exception handling for the same thing. Awful thing, you don't ever do that, but know how it works. So when you are running a, like, that's again a bad example. I cannot. Say you want to do something if you have memory failure. So you try a function that is handling memory, and then you catch whatever is underneath. So what happens is that if that memory handling went bad or leaking, you cannot detect. That doesn't throw exception. But if you try to, that's the alarm for the end of the class. Yeah, so you put all your memory management stuff in a try statement, and in catch, you gracefully exit your program, which means that you don't want it to crash. You want to save your data and stuff before things happen. You can do that. Okay, but exception handling again is for that. I keep putting stress on it, that exception handling is just for exceptions, not for everyday coding. Okay? Are we okay? Questions at home, people? Suggestions? Assignment number 2 was up. I set up the submission configurations, so you know what it is. And it's exactly like the other one. It's due at the Friday. Everybody's due on 2nd. I put it at the end, so we have like a few days more, because we are behind. Everything is good? Shall we?
We have a quiz for this lab.
You had a quiz week before, right? So the week after is the week before the midterms, right? I'll let you know today. If I don't do a quiz now, then I have to do 3 quizzes after the thing. Maybe it's a good idea for me to do a quiz, so you study for you prepare for your midterm. So I'll let you know. I'll let you know in a day or 2. All right. Have a beautiful day, everyone.